Welcome to the PH4410 review of correlation filtering. In our previous video review of random matrix theory, we have seen how the eigenvalues of the correlation matrix can be separated into signal and noise according to predictions from the random matrix theory. Now, but that tells us, and we have also gone through a review of the information contained in the eigenvector of the cross correlation matrix if it belongs to the signal. Of course, if it does not belong to the signal part of the eigenvalues spectrum, then it contains no information whatsoever. But sometimes we don't want to go through the trouble of actually diagonalizing the cross correlation matrix, but just to actually examine the cross correlation matrix. In this case, we see that of course the cross correlation matrix must be symmetric, and it contains n times n minus 1 divided by 2 independent matrix elements. Okay, so that's a very large number of independent matrix elements, especially if n is of the order of a few hundred to a few thousands. This is a huge number of independent matrix elements. Some of these will be small, others will be large. We will mostly be interested in the large correlations because those are likely to be associated with signal from the market. But how do we pick out these kind of large correlations? If we go back to random matrix theory, okay, we can actually make use of the diagonal form of the correlation matrix. So this requires us to diagonalize the correlation matrix. So this will be of this particular form: sum over L going from 1 to n of UL factor dagger lambda L UL. Okay, so this, okay, or the other way around. I think the transpose should be on the other side to give us a matrix. Okay, so the transpose should be here. So this is the diagonal, this is the spectral decomposition of the correlation matrix. And we can actually make use of this to do filtering. First of all, if we plot the market mode, so this will be I, and then we see that for the market mode, we find that most of the eigenvalues are about this level. But if we go to say a noise, an eigenvector associated with an eigenvalue in the noise part of the spectrum, then we might see something like this. Okay, so this is the components. These are the components of UL in the noise part of the spectrum. And then of course in the signal part of the spectrum, what we find is that first of all, the noise part of the spectrum defines some kind of a noise level in the components, and we can transfer those noise components over here to the signal eigenvector. And then of course when we go to the signal eigenvector, we will find now, of course, there are still components that which are below the noise level, but then we will find every so often components rising above the or below the noise level. Okay, and these will be what we are interested in. So this particular components these are the components that we will be interested in, and so these will tell us, these will allow us to reconstruct the correlation matrix so as to pick out those components, those stocks that are important in the market. So if we do it this way, then this is called spectral filtering, but this is not the only way. In the next video review, we will go through first threshold filtering, and then followed by the minimal spanning tree and the planar maximally filtered graph.